morning, good afternoon. Can you all hear me? Please type any message if you cannot, and then we might help you with that. So today, it's a wrap-up session. I'm just going to be looking at the solution of the problem that I posted yesterday. I think a lot of you were at least on the right direction. I wasn't able to compile and run all of you and debug all of yours because it's a very short time, but I did go through most of them, and it seems on the right direction, and I'm gonna comment on that soon. Then after I'm done with the diffusion equations, and please ask a lot of questions when I'm going through the solution. Then I would like to talk a little bit about non-blocking communications, and then open again for more questions, okay? So the scientific example, I'm just repeating the slides just as reference. We're doing the composition of the domain using MPI, and then you have to discretize the diffusion equation, right? And to compute the derivative on every single point, I need, for this example, three values at the point that I want to compute and the two neighbors, left and right, okay? And if I want to do this computation on a supercomputer, usually it's not going to have enough memory to run the solution in one node. So I need to decompose the domain. And since the derivative always needs neighboring points to be computed on any particular point, when you reach the boundary of the domain, you're not going to have that information readily available. So we had to introduce what is called a guard cell or ghost cell or ghost point. The nomenclature varies a little bit in the literature, but the concept is the same. It's basically a cell that you add in addition to, your domain, to your grid, such that you can impose boundary conditions or use as a way to exchange data when you do a domain decomposition of your problem and submit this problem to several different computers, to several different, with several different processes to do the computation. So basically, the guard cell, you need to exchange between those, okay? And I mentioned briefly that in 2D and 3D, there are different ways of doing this decomposition, but usually we are going to do as we did for 1D, or most of the problems as we did on 1D, because it's simpler, and that's how you're going to see most of the problems that you can find on the web, right? But you always want to decrease the ratio of the surface to the volume, okay? And I end up with the diffusion equation code. So let's go and look at the solution. Basically, you have to start with the MPI, we initialize and finalize those usual MPI call functions, right? Find out what is the size of the communicator, the rank of your task. And then the tricky point is to work out what is the local points, how many points are going to have, and be careful at the end because this number might not be divisible by each other. And then you have to figure out who are the neighbors of each task, right? And then you start by sending the data. And then you start to send the data between the neighbors, left and right and left, okay? And then you exchange the guard cell, okay? Let's take a look at the diffusion equation. So, what is going to be the best way to do this? I think I'm going to, okay, I'm going to do the following. I'm going to compare the serial code against the MPI code so we can see where the modifications are. And then I open the MPI code again and then do a pass to clarify exactly what I'm talking about. Let's see if this works fine. Okay, can you all read on my screen? Is the font appropriate or should be a little bit larger? Okay, that's good. I'm gonna make the code available as well, so don't worry about this too much. So I think the first thing that we need to do, of course, is to include the MPI headers with the MPI function call prototypes and data structures declarations, right? So that we know that we are calling, your code knows how to resolve the symbols that we need for MPI. And then we need to introduce the local points, because now each domain will have a local number of points, right? The initial domain has a total number of points of 1,000. Now your local number of points might vary, depends on how many processes you wanna run with, okay? So I saw that some of you hard-coded these numbers. I would suggest not to do this, because then you lose the flexibility on how many processes you want to do, or how you're going to scale the size of your problem and so on, right? Even this total point equals to 1,000 here, it is sort of hard-coded, and I would not recommend to do that as well. Or pass as a parameter and then broadcast afterwards. But at least the local number of points should not be something that is fixed. It should be computed on the fly based on the total number of processes or tasks that you are using, okay? And then you have the float number, local left, local x left, local x right. Now remember that you have the rod, right? And then you're subdividing those domains, and then you need to know what is the x value of each of those subdomains, okay? So basically that's the main thing that you need to do in terms of define the parameters for the local domain. Okay, now let's go down a little bit. You have to define also the global error, not only the local error, but also you have to define the global error when you are going to do the reductions. So you know what is the error in the whole domain that is distributed on the several different processes. And here we start the MPI stuff, right? Usually the error, the rank, and the size. The start and end is just basically two integers that will label where is the start and the end of my subdomain, okay? I think it's going to be clear a little bit lower down there. Left and right is going to be how I identify my tasks that are on my right and what is the tasks that are on my left. And we have to do two kind of communications. You're going to send to the left and receive from the right, send to the right and receive to the left, okay? So to distinguish those two kind of communications, you have two tags, left tag equals 1 and right tag equals 2. You have the MPI status, that's easy. MPI initialization, you're already familiar with this. Communication, the size of the communicator, how many tasks I have. If you run with 4, it's going to be 4. And what is my task ID, identification, my task ID, that is called rank. Fine. Okay, how do I compute the local number of points? I just basically take the total number of points and divide by the size of the communicator, or how many tasks I have on my communicator, okay? Those two numbers are integers, so what you're going to have is a division of two integers and will be loaded as an integer. There is going to have a remainder, right? Because the total points and size are not necessarily divisible. Total points is not necessarily divisible by size. So you need to handle this number of points, this local number of points at the end of the domain. Okay, you're going to see in a minute how you do it. Basically, the start point is going to be just the rank times the local number of points. So basically, if you rank 0, the start is going to be the index 0 here, And then the end is going to be the rank plus 1 times the local number of points. So for example, if here we have the total number of points equivalent to this, you're just going to rank 1, okay, minus 1. So you just get the last one, and that's where it ends in terms of the indexes on this global array of 1,000 points, okay? And of course, here we have the exception. If I'm the last task of my group, right, the size minus 1 task, then I have to set the endpoint to the total number of points minus 1. Okay, so now the total number of points here minus 1. Because the last piece of the decomposition might not be equal to the other ones, because the total number of points might not be divisible by size. Okay, so that's how I need to do. And then I need to update the local points by taking the difference plus 1 between the endpoint and start point minus 1, plus 1, sorry, just to make sure. So right now, I basically define the local number of points of all domains. Everything that I need to do now is to compute everything locally using this information, okay? Of course, we have to find out who are the tasks that are on our left and who are the tasks that are on our right. So the task on the left is just rank minus 1. The task on the right is just rank plus 1, okay? And the special cases, when you reach the task at the most on the left, then you put MPI prof no, meaning that you don't care about that communication. It sends to a black hole, to nowhere, to the no. And the same for the size, as we did before on the simpler example. Okay, so let's keep going. Any questions about what I just said so far? What is the difference between what? And equals to total point minus 1. Okay, let's say you have 1,000 points, as we have here. And if I take the size of 3, right? And a size 3 will have 1,000 divided by 3. It's going to be 333, okay? 3 times 333 plus 1. So the first two domains have 333 points, and the last domain will have 334 points. So you need to take into account this difference, because 1,000 is not divisible by 3. It's not exactly division by 3. Okay, so that's the reason that we need to take care of this kind of that's the reason we need to take care of the remainder of this division. Okay. Okay, good. Let's keep going then. What if size is 7? Oh, you do the same computation. So 1,000 by 7, how much is that? Do I have a calculator close by? So 1,000, 142. So if you do 142 times 7, is actually not 1,000. So 1,000 minus 994, you have an extra 6 points that you need to take into account. Okay, so the other domain is going to have 142 plus 6. The latest domain is going to be 148. Okay. What if size 7, for example, 14? what is the 14? I'm not sure I understood this. You just divide 1,000 by 7, and then you have 42 as the main. You can have like 6 processes, 6 tasks with 142, in the last task 148. Yes, it's not 100, it's 1,000. Okay. So are you calculating x left and x right local divisions of minus 12 and 12? Oh, let's get there. Let me get there. If I don't answer, I'll go back. Okay, so then you have here the x right. Okay, this is the same right as the diffusion. I know the size of the spacing and and how I am going to march in time. But then I need to define what is the local x left and the local x right on each of these subdomains that I did the decomposition. I basically take the x left and add the start. The start is an index on the global domain, right? That we just computed up here, times the x, and then I'll have the value of the local x on the left of the subdomain. The same for the right, okay? Now here's a point that I saw a lot of you making, is the following. You kept allocating memory for the whole global array. So please don't do that, because the whole idea is that you need to work with local arrays, because the global array in a production system, in a production simulation, will not fit in memory on one compute node or for one MPI task. Okay? So instead of using the total number of points as it was used on the original diffusion equation, now you should allocate memory for the arrays only using the local number of points. And the idea here as well is that for every single local array, you also allocate the ghost, the guard cells at the same time, the same way that you did on the serial code of the diffusion equation. Okay. For the 7 process example, is it better to allocate 1 from 6 extra to each process? Yes, you could try to work out something like that as well. Yes, you could definitely try to work out like that. The problem is how are you going to generalize this? So for this case, for 7, yes, it works fine. But what if you have 13? You know what I mean? So does your math to select this way generalize? It is possible. I just have not thought on how to do it. You might have done that. If you want to share how you did, that would be good. Because as I said, I could not see all the details of all codes. But that's one way of doing as well. I opted for the simplest one. That is basically I take care of the number of points that is left and add on the last subdomain. Okay. But you definitely can do some heavier work on balancing the load with all the processes. Yes, we'll have a better performance. Yes, it has a chance of having a better performance, not necessarily for this 1D case, because the amount of computation that you're doing with respect to communication is really small. But as you go to 2D problems and 3-dimensional problems, the amount of computations with respect to the communication becomes quite large. So you want to make sure that the work is well balanced. So if you don't do this kind of things that you are proposing here, yes, it will matter. You're going to see that a lot of tasks will be waiting for others to finish their work, such that they could communicate. Okay, so yes, load balance is a good thing keep in mind. I would suggest to always go by parts. So the first thing is make sure that your code is correct, right? It's well written, it's modular, so it's easy for you to modify and to swap routines if you need. And then later on, you do try to do your optimizations or reorganize the communication pattern to become a little bit more efficient, rebalance the workload, and this kind of thing. Because if you do this on the beginning, you risk getting lost and getting a wrong answer, and you don't have a code base to compare the wrong answer. So have a code base that just works, just gets you the right answer. And then later on, you write another one similar to that one, and you keep doing your optimization, reordering the pattern and so on. And you compare the solutions, right? You compare the solution between the simple basic one and the other one. So you can have, you reaffirm that your solution is correct, that your optimization does not make the code runs incorrectly, does not give you an incorrect answer, okay? Yes, I think Ramses also suggested something else here that you could try. Yes, as long as, yes, okay, as long as it fits in the long integer, okay? Okay, so let's keep going. I have the arrays here. Don't worry about pgplot. I mean, you can change the values, but not for this. It's not relevant for us right now. Excuse me. Here is the main computation. So as you can see, now I'm doing the steps, and I change the boundary. I fix the boundary conditions with respect to the local points, right? So if you are the first and the last one, you're just going to get the boundary condition, right? But if you're in the between, you also are going to get these boundary conditions. However, those guard cells are going to be rewritten when you do the MPI send and receive that I'm going to show you in a minute in more details, okay? So you're going to do send and receive rightwards and leftwards. And then afterwards, you do the computation. You loop over the local points, compute the value of temperature, and later on, you compute the theory, the value of the theory, also always looping on the local points, okay? And finally, you do all MPI all reduce of the error. You do the computation of the error here, and do an all reduce of the error, install the global error, and then basically you take the square root of the global error, and you have the error that is printed to the screen, okay? Now let me, basically that's the difference between the two codes. And of course you have to MPI finalize at the end, okay? Now let me just open the solution to be easier to read. And I think I need to go back to MPI send and receive. Oh, wait a minute. First, I have one question that I might have not addressed. What is the question that I had? Okay, you're not calculating x left and x right local divisions of -12 and +12. No, I do the divisions on the indexes, right? Not on the values themselves. And then I use those indexes to compute the local x left and local x right. Okay, Maddie? I think now I understand your question. Please let me know if it's not clear. What else we have here? Does it matter if the send receive occurs after the finite difference computation, and it communicates the temp new data. So you have a send receive after the finite difference. Well, no, that's a problem because the interior point needs the value of the boundary, right? Let me show you here this. Yeah, right. So if you do this computation from 1 to 5 and then exchange update the cells, you're going to miss the value on 5 that depends on 6 will be wrong. Okay, because it's not updated. It's not updated. So you should update those values first. Okay. We're going to talk a way of overlapping communication computation in a moment, but I just want to make sure that for this problem right now, the way that we are doing, it's not possible because the value of 5 will be in that finite difference computation and we'll need the value on 6. And if you have not updated that value yet, it's going to be a wrong result for 5. Maddie, what do you mean that it only matters in step 0? What I just said? No, I think it will matter on every single step. Because on every single step, you need to loop from 1 to 5. So if you loop 1 to 5, you are necessarily accessing data on the guard cells. And if that data is not up to date, you're going to be using outdated data. So it needs to be on every single step. After swapping new, it will be reflected in old in the next step. Yeah, but it's going to end up being 2 steps old. Right? Unless I'm missing something. Maybe we can read in the code and double check. Okay, let me finish this MPI send and receive to see if everyone understands what is going on. So I'm going to send the data rightwards. So basically I have, let's say if you have a subdomain here, and it's going to send the old, what I can say here. This is the end of that domain, okay? That subdomain, the local points here. It's going to send one MPI float to the right, and we have the right tag, okay? And the other domain will have the temperature on 0. it should be, excuse me, it should be receiving on its first point, on its guard cell here at 0. Sorry. One float from the left. Okay, so that's how you send up to the right and make sure what you're sending is being matched. Okay, so one process will hit this send and receive. Another process will also hit this send and receive. And then the one that is sending to the right will be matched to the one that is receiving from the left. Okay, and the same idea for the data on the left. So here, the first element of your subarray will send to the left. Okay, and in another subarray will receive on its guard cells from the right. Okay, so that matches. I mean, I know it is confusing because you need to really draw what is going on here, but that's how you're matching the communications, right? It's not MPI send receive is not related to just one process. You need to see how each statement is being processed on every single process, right? And the one that sends to the right needs to be matched to the one that is receiving on the left. And the one is sending to the left needs to be, yeah, the one that is sending to the left needs to be matched to the one that is receiving from the right. Excuse me. Okay. So basically it's this, and then here we do the normal computation of the interior points. It's running from 1 to local points, right? Not to the guard cells. The guard cells were already exchanged here, so it's fine. March in time. Of course, update the correct solution. Compute the error, the square of the error. Then you do the MPI reduce of the local error, because every single process is hitting this statement and is computing this value locally, right? And then you need to reduce and put that result into the global array, and the reduction operation is just MPI. It's just a sum of those values of the errors, right? And then you sum and put in the global error. And then you take the square root of the global error to know what is the error that you have. And then if you are on the rank 0, you print that familiar output that we saw before. Okay? And basically that's it. Then we swap the levels and do another step 100,000 times and finalize afterwards then. MPI finalize. Okay? So basically that's the solution. I mean, if you run it, I can do is run 4, for example. Diffusion, CMPI. It takes a few seconds. I see there was a post on the forum saying that, oh, it's taking 5 minutes. So if it is taking 5 minutes and no return, that means you probably have a deadlock. So you need to inspect the code first. Data, right? Of course, here I forgot to take the PGP plot compilation preprocessor flag, but it is not a problem for me here. And then I can see the error that I get that is similar to the error that I get on the serial code. Okay. Excuse me. Do you guys have any more questions about this solution? No, what's the time? We still have time. Can you see more about DPG plot? What do you want to see? Well, I'm not sure. For the parallel version, it's not really useful, right? Let's see. Because the way that is doing the PG plot, if I do the same thing that I did, I don't think I'm gonna be able to do. Let me see here. It might work. Let me do with MPI run on the login node, which I do not recommend. Of course. Let me just set up. Yeah, so you see each PGP plot opens a window, each process opens a window, and then that's what I got, right? So it's not very useful for this particular problem. I think Ramses is more familiar with this than I am with the pgplot. Oops, and the plot. Yeah. That's a good question. I used to use on my PhD work. I used to use XVS. Let me get the page for you. But I mean, but yeah, I think if you want in one window, you probably need to put the total points. I don't know how to do that on pgplot. It is possible that you can do that. But I really don't know. Do you know, Ramses, if it is possible to put in one window? Yes, yes. But suppose that it doesn't fit in the code, it doesn't fit in memory, right? So if you have truly parallel, because MPI gather, I could put everything in one node, but if it doesn't fit in the memory, then you're in trouble. You might have to sample that data before sending. Yeah, okay. So maybe we should work out an example like that for the pgplot. I don't have on top of my head. Yes, the graphics will definitely take longer than the computation. What I use, I mean, this tool here, XVS, is for one dimension. What we usually do, I dump the data, the solution on file, and then afterwards, I would load that file to the visualization software, and then do whatever I need with that file. Do any kind of transformation on that data, inspect any data point. You could do step by step over the data. I mean, you can do a lot of things with that data, right? With the visualization software. Let me get the where I was. Give me 1 second. I'm going to post the link. So in terms of visualization, this is the software stack that I used to use. In particular, the XVS. And you have the, for 2D and 3D data, I used to use DV. For 2D and 3D, and XVS for one-dimensional data, okay? We have Paraview, we have, what is the name of the other? Visit, that are more modern tools used for visualization. And I think Marcelo is more familiar with those tools, and then he can help you with visualization. The tools that I mentioned here are sort of like hard to compare because it depends on XForms, and XForms is old and ancient graphics interface, graphics primitives, and modern Linux computers don't usually have the most modern one, and so it's a bit of a pain. But once you get them to work, it's beautiful because you can have control over the data, and you can zoom in, zoom out. I mean, it's amazing. I love those tools. I mean, if you want to, really get serious and compile those tools, please send us a message and I will help you with that. I might even install on Cynet or Niagara. Could we access solution anywhere? Okay, let me change the Cynet course summer school tutorial. I think it's for MPI. Selected and the preview, you can see here. Yes. So change one. That's good. Okay, you should have access to the solution, to all the solutions. I open all the solutions. Okay. Let me see the questions I missed a little bit. Okay, when you're creating the left and right, near the start of your MPI code. Okay, let me go back to the solution. Okay. Diffusion C, okay, so why you don't understand? When you're creating the left and right, okay, just, so MPI initialization, left and right. Is this what you're not understanding? Fifty-one to 60. Okay. 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 So, okay. So, should I draw? I don't know how I'm going to draw this. So the rank is the task identification. Yeah, okay. I'm gonna give a try with the whiteboard if I can find here. There is a whiteboard. No, I'm sorry. What can I do? Let me just share options. Oh, I see. Should be new share maybe. Whiteboard. Okay, let's try. Because I'm having to draw with my mouse, and it's a very weird thing. Okay. Oops. How do I get like that? All right. So what do we have? We have the start. Yeah. And then end. And then you have another one like this. And so on. Okay. Let's say three. We have a division by 3. So this is the start. And then we start at 0. Oh my goodness. I'm sorry. And then goes to, I'm going to call, just because I cannot write very well, I cannot see them. total points. Okay, I'm sorry, I'm trying this new. And here you're gonna have the local points. I'm gonna just call log. I can maybe use this text. I can erase these guys and do. Yeah, let's use text. Yeah. No, why it's even not. No. 0. No, it's not working. It needs to be drawing. Sorry about this. What is my pen? Okay. So here is 0. I'm going to call this L. And I'm going to call this T. Okay. So you go, your start is here. And then you want to end here. And then you want to start here and then here. Okay, and the same here. So the first one you have, the start is going to be rank times the local number of points, right? So the first one is going to be at 0, so you have 0. The second one, the domain is the rank is going to be 1, so 1 times the local number of points. The local number of points is going to be, it finishes here, right? The last cell here is L minus 1, right? Because it starts from 0. If you do L minus 1 minus 0 plus 1, you have the L, that is the total number of local points. Okay, and then as you multiply that for the rank, you're going to start the first on the first point of the local domain on the next rank, and so on. Okay, you multiply you're multiplying by the local points. And the end that is here is basically the same computation that you did, but for the next rank, right? You type the rank plus 1. So if my rank here is 0, and then I have rank plus 1, I'm going to land on this point here, which is not the end, right? It's the next point, the start of the next point. So I have to subtract 1 to be the total point, okay? So this computation works fine on these domains here and there, but on the last one, because it's the total points might not be divisible by size, so I need to put the end on the total points minus 1. So the end to be here, okay? And then I can recompute the local points by just doing the subtraction of the end minus the start point plus 1. If you do this like L minus 1 minus 0 plus 1 is L. So I have the number of local points here. And if you do this, the same thing here, right? It would be like a 2L minus L, that is L minus 1, plus 1 is L, the total number of local points. Okay? Is that clear? I mean, you can use the voice if you want. Okay, let me try to go back. How do I go back to my other shed? I'm sorry, I'm trying to get back to this. Let me stop sharing and share again. Oh, I see. Sorry. Okay. So I'm rereading the questions because I might have lost some. Okay, is it considered good form? Okay, I think it's clear. Also, it was understanding how I decide what is being passed between iterations. Okay, so if it is clear, fine, thank you. So if it is not, please let us know again. I'll try again, and then we can use voice, maybe it's easier. So Joshua, is it considered good form to hard code send count in MPI send receive? Um, I think it depends. Yeah, usually I would say no. Do not hard code anything there because it's easier to change one parameter, right, instead of the code. So here, right, you're talking about this guy here, one MPI float. Yes, I don't think that's the best form. Uh, it's not like the end of the world, but usually it's better not, because if you decided to have two boundary conditions, you might have to send two floats or something different, right? So usually on the function arguments, it's not a good idea to hard code, okay? This is a simple example. Uh, I think it's just easier to visualize, but yes, it's better to just set a parameter of, I don't know, n floats or whatever, and then deal with that on the code. Because whenever you need to change something, you change just in one place, right? One parameter and then change what you're doing with that parameter everywhere. How would I not hard code? Well, I mean, this is a simple integer, right? You just define integer n count or something like that equals to 1. And then you type it in here instead of 1, you type n count. You don't need size off because it's a simple data. You're not, you don't need to allocate this simple data on the heap. You can just allocate on the stack as you go because it's small. Yes, attendance code today 6. Okay, let me see if I missed any question. Okay, Maddie, are we using total points anymore? Is there any difference if we do only total points and leave the other equations as it is? Which other equations? I mean, you're doing everything is being worked out on the local points, right? You do just here on the beginning to see what is the local points, right? If you if you if you look for the total points, you're gonna see that is used basically to define where is the start and the end and the local points, right? And dx, and basically that's it, right? The rest is on the pgplot statements that we're not interested here. So I'm not sure if I understood your question. Yes, but Joshua, you cannot guarantee that. I mean that's okay. I mean, you can always say like, yes, I'm going to run this code always with an even number of processes. But it's better that it's a little bit more general. That if you need to run with an odd number of processes, you can. Oh, you mean omit well, no, you cannot omit immediately because you do need to compute the total number of points like that. Unless, as Joshua is mentioning, you get rid of this because you're going to use always even. No, but even if you use even, I mean, the number of points of the domain, okay, you need to be careful because the number of points of domain you have always should be even if you're going to get rid of this part, for example. Then yes, if you omit the total points, I mean the definition of the local points. But I mean, it's better to be explicit. Okay. So I would like to go back to the slides. If you don't have any more pressing questions about this solution, I will go back to the slides and then we can go back later on to any further questions that you might have, okay? Okay. So non-blocking communication. What we have seen so far was only blocking communication. And what do I mean by that? Those are computations, those are communications that when you do MPI send and MPI receive, they do not return the command to the calling function. They basically need to wait until that communication is finished before returning to the command, before returning the control to the calling function, okay? So the MPI non-blocking communication function is a mechanism to help you overlap the communication with the computation. And at the same time, to avoid any deadlocks, even if you, by mistake, would have one, because you are doing this overlap, you would avoid this deadlock. So, and on top of that, you can avoid also the system buffering and memory-to-memory copy and improve performance overall, as we're going to see. The basic idea is that when I do these MPI functions, MPI I send and MPI I receive, it's going to return immediately. It just requests the communication to start and returns the control to the calling function. The communication is not complete when it returns, so you just the request, it just initiate the communication, and because it is not complete, you need to be very careful with the buffers that you are sending the data. You should not touch those buffers before the communication is complete, okay? Otherwise, you're going to have an error. I mean, if you modify the data on that buffer, that data is being sent, so maybe part of that data is going to be sent modified, right? Which is not what you want. So, for example, the diffusion equation, you had to wait for the communications in order before the exchange of the guard cells finished before doing the interior points, right? The loop and the computation of the interior points, because the interior point at the end would need the value on the guard cell that belongs to the other domain that is being computed on the other task, right? And the same here. So what happens is that every single work here, every single work would not be done. Everything will be halted, everything will be idling, right? Waiting for the communication to finish. So it is a significant parallel overhead, especially when you go to 3 dimensions, and especially when you have several guard cells to do the computation. I'm sorry. Yes, it's... So, but did this did the computation really need to wait? And my claim is no, you don't need to wait. Basically, you just initiate the communication here, and then go back, do the computation between 2 and 4. You can do the loop here because this is not going to depend on the data at 6, right? But you need to be careful because you need to finish at before 5, because 5 will need the data at 6. So basically, you initiate your communication, your exchange of data between the guard cells, go back here in the loop, do the computation 2, 3, and 4, and get back and ask, oh, hey, did it finish this communication? If the communication is done, then I go back and compute the values on 5 and on 6 here, and then I'm done with the problem. So this is basically an overlap of the communication with the computation, okay? So the sequence happens as follows. We start the code exchange with the guard cells, like we send receive, right? That's the blocking communication. You basically, you send your data and you're waiting for receive. The data goes, flies, get back, send receive, everything shakes hands and say, yes, the communication is done. Let's go back to the computation and then do the computation, okay? And then the next step comes back and then you do the send receive. You wait for receiving, you send the message, it flies to the other process, and then the receive, it happens, shake hands, everything is fine. Let's go and do another computation, okay? So you see that it's not overlapping, it's blocking. You do the communication and the computation in sequence. There's no parallelization between them. However, we can do better. If you do a non-block communication, like I said, for example, if you start the code by sending the guard cells using the ISend, right? So you basically, you start the ISend and it returns to the code, the control, and then the code can start doing some computation while the message is on the fly. So it is in parallel, okay? And then eventually the message hits the task that is waiting to be received, okay? And then both of them receive, and then go back, do the leftover of the computation, and repeat the process. Send the message, get back the control to the calling function, do computation, the message and the computation and the message are done executed in parallel, so on the fly. So you're overlapping the computation and communication, receive, go back and do the leftover of the computation that you need, okay? So it is great to increase the performance of your code, because now if you have a lot of computation to do, that can be done in parallel with the communication that needs to be performed, okay? Non-block sendings is just the function prototype that I'm showing here. It allows to get the work done while the message is in flight. It must not alter the send buffer until the send has completed. So the send buffer is this guy here, right? Whatever pointer you send with ISend, don't touch it after you send with ISend. Don't touch. Wait for the communication to finish. And the function signature is very similar to the other sends, right? You have a count of the data type. You need to tell the destination, a tag, the communicator, and then we add a pointer to an MPI request data structure here that will take care of the communication request that you asked, okay? The same idea for Fortran, but then with an extra arrow being sent and retrieved on the argument list. So the MPI, I send and I receive the signature here. What I have to say, I think I have said already. So send buffer, receive point, send pointer, receive pointer, those are the buffers that you need to not touch while those two functions are called. It sends a counter MPI type that can be double, float, integer, character, your defined type, and so on. Destination of the source, and destination and source is the rank of the sender and the receiver. A tag is a unique ID for the message pair, right? So they can be identified if one task sends a lot of messages. Communicator is the MPI common words, that is the default communicator, or can be the communicator that you define. An MPI requires us to identify the communication operations. I think you're going to see in a minute. And of course, okay, I send, and I have the other code with I receive, and then the request to communicate has been done. And how do we know that that communication is done? That's the question that I think James just asked, right? And we have two ways of doing that. One is doing with the MPI wait, and then basically it's a blocking operation, and it will block any further. It will block the computation of the code, the execution of the code until all the messages hit, until all the communications are finished. So the MPI wait will just look at the request and say, okay, this if this communication is done, let it go. If it's not, we have to wait until that communication is done. And MPI wait all is for, it uses an array of requests. I think I was basically saying about this, not MPI wait. MPI wait would be for each particular request, while MPI wait all is going to block all MPI tests until all of them has the communication finished, okay? And basically the signature is a count of, and this count here is just the number of elements of this array of requests that you have. And you have to return an array of status as well. The same sort of signature for the fourth run, okay? We have also MPI wait any and MPI test. The MPI, okay, MPI wait all, I think, yeah, I should change the order here. So yes, the MPI wait will block the communication until it's complete. And the MPI request identify the communication operators. MPI status, the status of communication operation. And the number will be the number of encounters, the number of communication operations. MPI test, it does not block. So you can have like some sort of like infinite loop doing the computations, and from time to time you just test if your communication has been done. And if it is not done, you keep doing more computation. And if it is done, you just stop and then leave that infinite loop, right? It's another mechanism that you can use to overlap communication and computation. Basically, the signature is very similar, but now you have a flag that will return true if the communication is complete, right? And false if it is not. So, and then you can test, okay? I had another hands-on to do, but I think it's very late, right? Only 20 minutes. What I'm going to do is I'm just going to compare the difference between the blocking and the non-blocking I/O, and that is the problem that we have. And then I will open to questions again, and basically that's the end of this wrap-up session. Let me go here, then diffusion, CMPI.c, diffusion, CMPI, non-blocking. Let's see if it's going to work fine. So now the MPI send receive that you see on the left here on the blocking code, it is a blocking operation, right? It's not going to return the control to the function that is calling until the communication here is finished, okay? On the other hand, the MPI I send and MPI receive will just return immediately, will post the communication request to the MPI library and return the command immediately. And so the MPI I receive will do the same, okay? So in order to keep track of these communications, you need to define here an array of requests and an array of status, MPI status, okay? So that's the first difference. Where you do the MPI send and receive, you're just gonna have to break the MPI send and receive between I send and I receive. I send and I receive to send the data left, send the data right, and to send the data left. Okay, we're going to see in details how it is here. Also, as soon as you send, the command come back. As soon as you put the request you receive, the control comes back and does the same here. and then the statement keep going, and now it's ready to do the computation on this part. Here, we would have to wait until the communication is done, right? On the left, we have to wait until the communication is done. On the right, we can immediately, after posting the communication request to the library, we can immediately start doing some computations, as long as it doesn't need to the data points that is being communicated. It doesn't need the data points on the guard cells, right? So that's the reason here that this loop, it loops over 2, the second point, to the total number of points minus 1, okay? So it is the equivalent of looping, where is that? Yeah. Equivalent looping from the number of 2 until the local point of the total number of local points, in this case is 5, the total number of local points minus 1, 4. Okay? And while this point is going to be computed only after the guard cells has been exchanged. The data in the guard cell has been exchanged. So the 6 has been received here. The data, the grid point 6. Okay? And once you're done with that, we need to wait. So here we have MPI wait all. We have 4 requests. For each of these communications is 1 request, right? This is the array of requests. This is the array of status, MPI status. Once that is done, all of them is performed, then we are ready to do an update of the endpoints. We have the computation of the endpoints. And then we do for the first point in the local for the last point, the local points. Okay, you update that point, and then the rest is basically similar to what we have before. So let's go back here to the diffusion C MPI nonblocking.c. Here. So the signature of the MPI I send is very similar to send, right? You basically will have, okay, I'm sending the data rightwards. So the last point here needs to go to the right, right? The last point of the domain needs to go to the right. And I'm gonna be waiting for, sorry, that's the I send, I'm sorry. It will send to the right here, and then we have the right tag. And the I receive will get the first guard cell here to get the data from the left, 1 float from the left. And then we'll be waiting for the data to be sent from the right, right? And you see that on each of them, I load the value of the request on the array of MPI request data structures, okay? In the same way for the data on the right, you send the data, your guard cell, sorry, I'm sending to the right. Your first point of the domain will be sent to the left, and you're going to be receiving from the right, and you're going to put on the last point of the domain, on the guard cell of the last point of the domain, the data receiving from the right. And each of them has a request, okay? So this goes like, you call MPI I send and returns, call MPI I receive returns, I send receive returns, and then go straight to this computation here, where it does the update of the temperature, and then stops here. And then wait for these communications that were requested to finish. Once the communication that were requested here finished, so this returns a positive status, a finished status, right? And then you keep going, and then you do the update of the first point of the domain that depends on the point on the guard cell at the left, and the last point of the domain that depends on the data point on the guard cell on the right. And update those 2 values of the temperature, and that's it. You update, you march forward, update the theory, compute the error, do the MPI all reduce, and plot the data, and that's it. Okay, very similar to the other one, except that you overlap the computation with communication. Okay. So Do you guys have any more questions? I think we can conclude this wrap-up session here. We basically reviewed the one-dimensional diffusion equation, how to parallelize that. That was the problem that we had to solve. And we saw a way of overlapping communication and computation by using non-blocking MPI communications, right? The material that I presented here today is usually covered in two workshops, like an introduction to MPI and an intermediate to MPI. And I just condensed a bit and went a little bit with a faster pace for these virtual sessions. If you are interested, when we have these workshops again, you are welcome to attend these classes again. It's going to be the same material. And I'll be preparing also an advanced MPI course where we're going to extend how to define our own data types, our own communicators, and maybe doing an application like MPI IO, or maybe doing something related to one-sided communication that I have not mentioned. And those are more advanced concepts, not so widely used by the practitioners, but it is there. And I think it might be interesting to have a course on that. And I'll be preparing this course and let's see how it goes. Still have to talk to my colleagues to see how we're going to remodel during this pandemic. But for sure, once the pandemic is done, this kind of workshops will happen. And there's going to be divided in at least three courses, three workshops, right? One introductory, that is basically what you did, and one intermediate, that is basically the diffusion equation that you have to work, and another one more advanced concepts that is still to be planned, okay? So that's a summary that I left here with you of the syntax. Please let me know if you have more questions. I think we still have some time. Yes, at least 10 more minutes. Is there any more questions that you want to ask? Please let me know. You can use your audio as well if you think it's easier. Okay, thank you. Oh, by the way, there is evaluation of the course that you can submit that you're going to receive. So please do so. This format is new to all of us and your feedback is appreciated. Yes, the course survey, the lecture survey.
Bruno, this is Joshua. Is it acceptable for me to ask a question through audio now?
Yes, yes, definitely.
Okay, my question is this. I've been using MPI as a part of an open source CFD package for many years, and I've never had to deal with any of the particular intricacies of the communication and so forth. It's built into the application.
Yes.
How does one go from these kind of simple tasks that I really appreciate the learning experience to actually using MPI inside a larger application? Because I imagine the majority of graduate students, and certainly my team, don't develop new codes as much as use existing open source codes. Would you mind commenting there?
Yes. For example, I wrote my own code during my PhD, right? But I'm a sort of an exception. A lot of people nowadays, they use some sort of a toolkit or some sort of package to do the computation. I mean, from one side is good because you can focus on your problem, right? You can focus more like what kind of physics, chemist, engineering problem that you have at your hand. and do this computation and perform this without a detailed understanding of the intricacies of the code. On the other hand, I think sometimes a little bit is lost, because if you don't understand this very well, right, you might do some changes in your code, or do some computations that assumes a certain behavior, and this assumption is not valid, because the code did not use. For example, if you're doing this kind of overlapping, right? And maybe you're not able to do that if the developer did not hard code this kind of routines on the code, right? So, I mean, I had a passion to dive into any code that I need to use. And the reason I developed this passion is because the more I understand about the code and about the assumptions written in the code, the less bugs I would have, the less mistakes I would have. So that was what guided me. And I mean, we can go and have a long conversation. I can tell you how that happened, right? I mean, using my tools, using some languages that my supervisor wrote, for example, and then I just tried to use it, and then I had lots of mistakes, and then 6 months later, once I understood exactly the assumptions that was implicit there, then I was able to modify those assumptions, right, and then fix the bugs that I had, right? So it is always a matter of how much knowledge you want to have and how much time you have in your hands, right? Because and it's sort of it is a balance, right? Because sometimes because you don't understand, you might get stuck for 6 months, a year, maybe sometimes even 2 years. Maybe you have to finish your PhD and not be able to fix all the bugs because you lack the understanding, right? So I think what you can do is do something like I did here, basics. You have a basic understanding. Now you can look at your package. Usually it is well modularized. You can look at the modules where it is doing the computation for the MPI, and sort of like draw a flow of what is going on of the function calls, right? How all the functions are being called, how all the flow of the computation and communication is happening, right? And if you have more time, then you can think about doing some more overlapping and helping the developers of the package to do some overlapping of the communication and computation, or maybe doing some sort of like a load balancing algorithm, implementing some load balancing algorithm on that package, right? Or at least call the attention of the developer for this kind of problem. But I think it's a good exercise to at least understand what are the assumptions that are in the code. Because once you just use it, this is lost, right? So it's very easy to make silly mistakes that will cost you a lot of time to find. Once you have more understanding of the code and what's going on, then it's easier to do less mistakes and to find the bugs, right? So summarizing, you do not necessarily need to go there and develop this, but it's a good idea to take some time to go and see how those routines stack together, right? How your module that you are using to do your computations being used in the background by the infrastructure, by the libraries to do this communication between the nodes. I think that's helpful. I think that's helpful. But I understand that your supervisor is not going to be happy. Then you hide from him for a week, and then everything is fine later. You understand better, less bugs, and he'll be happy. So So I hope my answer is not so contrived because it is really a balance that you need to strike. Any more questions? Oh, okay, sorry, I think I missed a few questions. Okay, how do we know that I send when I receive is finished? What industries? Okay, I think I have answered that with the request, right? You can use MPI wait and wait all or MPI test or MPI test all, I think. And that's it. What industries use MPI outside universities? I think any industry, engineering, any industry that is heavily based on engineering to do simulations, modeling, large-scale modeling, they are going to use this kind of MPI. I don't know why the machine learning, the industry that is using machine learning didn't build on top of MPI to do the communication. They start with MapReduce, right, and then Spark, and all those, in my view, a little bit of a nonsense, right? I think they should have built on top of MPI. They might do something related. I just attended a seminar, I think it was yesterday, about some library that MPI uses to launch process, like it's called PMIX. And they are talking to the machine learning folks and neural network folks, and the AI folks, in order to launch their processes faster. So you see, like one piece of the infrastructure in MPI is actually being used elsewhere, right? But that's not common knowledge, common practice yet. So I don't know, people like to reinvent the wheel as well, instead of just contribute to a mature library like the MPI. What else? In a send receive, do both tags need to be the same? If it is the send receive, that's a complicated question. Because it needs to match, right? Maybe there is a case where on the sending side, you have a branch, and then you want to identify the tag differently. And then on the other side, on the receive side, you have a branch where you have send and receive. And then you might have that tags swapped to do some computation, depending on the different initial conditions. I could not find a good example where they are different. Okay, specifically for the send receive MPI underscore send receive call, right? Because the MPI send receive call will match the tasks, not only from where it's coming from or where it is going to, right? But also with the tags. And if one process of one task is sending several different messages with different tags, right? They need to be matched somehow. I'm still looking for a good example of that case for this specific function. But yes, in principle, it does not need to be the same, but you probably would have to have another MPI send receive to deal with the other tags. Okay. So any more questions? Yeah, Joshua, yes, go ahead.
My question is, can there be a workshop perhaps scheduled in the future focusing on debugging of MPI codes? Because I know that parallel debugging is kind of its own beast relative
it's a
to
help.
serial codes.
Yes, I'm not sure. Usually in the summer school, I have a session on the debug that usually I go over the MPI debugging a little bit. But this session, there's going to be a session on the debug, I think in August. And my colleague, Eric is going to be the lecturer. I think he's going to talk about MPI debugging as well. I'll have to check with him if he's going to change anything, but probably he will do some parallel. I don't know. I'll check with him. Yes, DDT is the tool that we use to do the parallel computation, and you can use that on Niagara, and I think on the Teach cluster as well. Yes. Yeah, DDT is really helpful because you can march in the code in parallel, and then you can see what each part of the code is doing step by step. So it is very useful tool. I do recommend to use that. The only drawback is that usually it's expensive. And then we have just a license for 64 cores, 64 tasks, and that's for everybody. So if somebody is trying to do some debugging at a little bit larger scale, it's not going to be able to do. But usually it is not used that much because, as you noticed, most of the time, once you're done with MPI, you don't touch it anymore, right? You use the package, you use the other people code or your own code, and usually you don't touch anymore. The communication, computation is fixed, and you just swap modules or add more modules to do other kind of problems using the same infrastructure. Yeah, total view is another one. I use in the test a little bit, but I don't recall anymore. We don't have it. We need to pay for that. We do have a DDT. Yes, and DDT can also use CUDA and GPUs and so on. Yeah. Total view is also a nice tool, but yeah, we need to pay for it. And then we decided for DDT a long time ago, even before I joined Cynet. And it's a good tool. I really recommend to use that. Okay, good. Okay, so any more questions? I think we have 2:05. So we should stop our session here. Please file your survey after 2 p.m., I guess. And let us know what we can improve, what was good or what's bad. And let's see in the next sessions if we can do a better job. Okay, thank you.